We all know that if the path of a particle is like this, then the velocity vector is necessarily in the tangential direction. For example, when the particle is over here, the arrow shown is pointing in the direction of the velocity vector. Of course, the assumption is that the particle is going from left to right along the path. Similarly, when the particle is over here, the velocity at that point, the instantaneous velocity, of course, would be pointing in the forward tangential direction. So this could be velocity v1 bar and this could be velocity v2 bar. However, the same is not applicable for the acceleration. For example, at the first point, it is possible that the acceleration is pointing in some absolutely different direction, something like this. I'll call that a1 bar. Of course, it is possible that the acceleration does point in the direction of the velocity. For example, here it could be that the acceleration points either in this direction or even in the opposite direction, a2 bar. But the point is, it is not compulsory. It is compulsory that the velocity points in the forward tangential direction. However, the acceleration has no such constraints. It could be in any direction. It depends upon the conditions. To understand why the acceleration need not be in the direction of the velocity, let us look at the basic equation for the instantaneous acceleration, namely a bar is equal to dv bar by dt. Here the numerator dv bar is the small change in the velocity v bar, and on the other hand dt is a small time interval in which this change takes place. Now this equation can also be written by taking the dt term to the left hand side. So what we get is the change in the velocity, the small change in the velocity during the time interval dt is given by the acceleration. It's the instantaneous acceleration at that time, of course, multiplied by the small time interval dt. Now let us represent this equation schematically, that is in the form of a diagram. Note that at some time instant t, the velocity is v bar and of course the acceleration is a bar. At a time instant t plus dt, a bit after time t, the velocity changes to v bar plus the change in the velocity, which is dv bar, and of course we have just said that this dv bar is nothing but a bar times dt. So I will now draw a diagram showing the initial velocity v bar and the final velocity v bar plus dv bar. So in this diagram, let us imagine that at time t, the velocity v bar is given by this vector, this green vector. I'll even name it v bar. Now let's take a simple case where the change in the velocity dv bar, which is of course a bar dt, is actually in the same direction as v bar. Note that this would happen, that is dv bar is in the same direction as v bar, provided that, now dv bar is nothing but a bar dt. So what we are effectively saying is that a bar dt must point in the same direction as v bar, and since dt is a positive time interval, that essentially means that this vector a bar is in the same direction as v bar. We are starting with a simple case where a bar is in the same direction as v bar. Now what I'm going to do is to draw this a bar dt, which is dv bar, the change in the velocity. Of course it's in the same direction as v bar, and I'll start it over here at this point. So a bar dt is this vector, it's also dv bar, it's of course a bar dt, and the reason why we have a rightward pointing vector, red vector, is that the acceleration a bar is in the same direction as v bar. Now if we try to draw the final velocity after the time interval dt, naturally we have to add the initial velocity to the change in the velocity. So I start from this point, and my final velocity, namely v bar plus dv bar, I could call it v final bar, is this vector, which is essentially it starts at this point and ends at this point. You can see that the final velocity is in the same direction as the initial velocity. Now let us consider a case where the acceleration vector is in the opposite direction of the velocity. So for example, I'll draw the vector backwards like this. This is the acceleration vector. Clearly the change in the velocity dv bar, which is a bar dt, will now point backwards, and so I'm going to change this red vector which I've drawn here. So what I do is I rub out the old vector, and my new dv bar is going to start at this point, and it's in the backward direction, it ends over there, and this is dv bar. It starts over here and it ends over here. Clearly by the triangle law, my final velocity is no longer going to be this big. It's going to start at this point and it has to end at this point. So I'll redraw my final velocity vector like this. And once again we notice that the final velocity after the time interval dt points in the same direction as the original velocity v bar. Of course, we could have a situation where the initial velocity is so small, so I'll just rub this vector out and I'll make it smaller than even a bar dt. For example, the initial velocity could even be 0, but I'll show it in the rightward direction. It's going to be in the rightward direction, but its magnitude, the magnitude of v bar, is even smaller than the magnitude of a bar dt. Now clearly when we add these two vectors, we get the final velocity v final bar, which would start over here and it would end over here. So it's going to be not this vector, it's going to be a vector now in the opposite direction of v bar. That's the final velocity vector v final bar. So what you could conclude from this brief discussion is whenever a bar is parallel to the instantaneous velocity v bar, whenever the instantaneous acceleration is parallel to the instantaneous velocity, the change in the velocity is going to be either in the same direction as v bar. So if for example v bar is in this direction, then the velocity will change like that, or it could change like that. Either way, what happens is the final velocity v bar final will necessarily be parallel to the old velocity, which was v bar. Now a special case where this would happen is when a particle is traveling along a straight line, and you know, in that case the acceleration, if it is present, that is, the acceleration would always be parallel to that line, and the particle would never leave the line because the change in the velocity is along the line itself. The particle would either move, if it's moving from left to right, when it moves from here to here, it would be either moving faster or slower, but it would never leave the line, since the final velocity is always parallel to the initial velocity at any time instant t. On the other hand, let's draw a situation where a bar is not parallel to v bar. My initial velocity v bar may be this vector v bar. Now let's imagine that a bar is at some angle to v bar, which is neither 0 degrees nor 180 degrees, like that. In that case, the change in the velocity, that is a bar dt, would also point in the same direction as this blue vector a bar, and so I'm going to draw the change in the velocity starting at this point. So I'll draw a bar dt, that's the change in the velocity, and clearly the final velocity after the time interval dt is going to start like that and it is going to end over here. So this is my final velocity, which I call v final bar, and that's of course equal to the initial velocity v bar plus the change in the velocity dv bar. This dv bar is of course nothing but a bar dt. Now the basic question is, for those who find it difficult to believe that a bar cannot be, or need not be rather, parallel to v bar, it can be but it need not be, is what is the basic reason in your belief that a bar must always be parallel to v bar? There is no reason for that. I can tell you why it's possible that a bar is not parallel to v bar by the following logic. Although we have not yet done Newton's second law of motion, you are aware of the law. When you apply it to a particle, the law is F bar is equal to mass times acceleration. Now remember, here when we are talking about the velocity, we have a particle in mind. A particle's velocity, the particle's velocity is initially v bar, and the acceleration is in this direction, a bar. Now if you do really want to generate such a physical situation, and all you really need to do is to apply a net force on the particle in this direction. So I'll write F bar here when the particle is traveling at this velocity v bar, and then its instantaneous acceleration a bar is of course a positive scalar multiple. Mass is positive, it's a positive scalar multiple of F bar, which would automatically imply that the acceleration points in the same direction as F bar. So the instantaneous acceleration of the particle at any point of time really depends on the direction of the net force, and there is no constraint that you are supposed to apply the net force only in the direction of motion of the particle. It could be at any angle to the velocity of the particle. It doesn't matter, it's up to you, and hence we can have an acceleration in an arbitrary direction, for example in this direction. Now we can even have a physical example where this happens. Let's imagine that you throw a stone into the air at some angle which is not 90 degrees. You throw it in this direction, let's say, and you know that the stone travels in a curved path like this. And let's assume for simplicity that you do this experiment in a lab in vacuum, so the presence of air resistance can be ignored. Now let's say that at some point of time the particle is at this point, and we know that the velocity of the particle must be tangential to the path, so of course the velocity, I'll denote it as v bar, is in this direction. Now let's try to find what is the direction of the acceleration. So we ask ourselves the question, what is the net force acting on the particle at this particular time instant? And clearly, because air resistance is absent, there is only one force acting on the particle, and that's its weight, and of course that acts in the downward direction, and you then can conclude that the acceleration must also be pointing in the downward direction. Of course, if we do apply Newton's second law, we can even find the magnitude of the acceleration, because F bar is equal to m into a bar. So what I basically get is F bar is m times g times minus j cap, because the weight is in the downward direction. Of course, I am assuming here that my y-axis is upward positive, and of course this is equal to mass times the acceleration. Now this simply means that the acceleration is minus g times j cap, or it means that the acceleration is the same thing as saying the acceleration is g, which is roughly 9.8 meters per second square, in the downward direction. Note that this particular fact, that is the acceleration is g in the downward direction, is true irrespective of the position of the particle, whether it is here or here or here or here, and that's because the force on the particle everywhere is mg in the downward direction. I can now get a nice physical feel as to how the acceleration actually alters the direction of the velocity. Now, for example, you know that when the particle is over here, the direction of the velocity has changed, because it must always be tangential, it must be like that. And if we take another point, let us say over here, the direction of the velocity must once again be tangential at that point, so it's going to be in this direction, like that. let's take another point over here. The direction of the velocity once again is in the forward tangential direction, so it's like that. And let's finally take a point somewhere over here. The new direction of the velocity is in the direction of the tangent in the forward direction, so I'll draw it that way. Now the amazing thing is our recognition that the acceleration of the particle is constantly equal to g in the downward direction can lead us to the general conclusion that the velocity's direction is going to change in the manner shown in the diagram. For example, let me draw the velocity at the time instant when the particle is over here. I'll draw it in a diagram like that. So I must draw a line segment, directed line segment, which has the same magnitude and same direction as the velocity vector shown over here, and this of course is equal to v bar itself. This I treat as my initial velocity. What I'm doing is the velocity at this particular time instant I'm treating as the initial velocity. Now just for our reference, I'm going to draw the acceleration vector which is in the downward direction, and this is a bar. You also know that its magnitude is a constant which is equal to g, so I'll write that in brackets. And now of course the rest is easy. In a small time interval, let's call it dt, the velocity changes by an amount which is given by, that is by a vector given by a bar times dt, of course pointing in the downward direction because a bar is downwards. And since this a bar dt is the change in the velocity, the new velocity is obtained, that is the final velocity after time dt has elapsed, is simply got by joining this point with the end point of that red vector like that. So this is going to be my new velocity after a time dt. Now after a further time interval of dt, maybe my a bar dt is a vector like that. I'll write here a bar dt. That's the further change in the velocity, and so logically the new velocity is obtained by adding this vector with this vector. This is now the first vector is the original vector and the second vector is the change in that vector. So needless to say, my new velocity is something like this. And in the next time interval of, let's say, dt, my new change in velocity vector is once again a bar dt, and clearly my new velocity must be like that. So what we can conclude is the initial velocity, which is v bar, after some time it becomes this velocity. So what you observe is the direction of the velocity has gone towards the horizontal. Let's not even concentrate on the magnitude, that's not the point. The direction has become more horizontal, the velocity has become more horizontal, and this trend seems to continue because the new velocity after a further time interval dt seems to have gone even further down. Now it's actually below the horizontal like that, and you can even confirm that the trend continues further by looking at this velocity, which has a direction which is even more below the horizontal, and clearly this indicates that the velocity, which was initially in some direction like that, is changing its direction as time proceeds. And in general terms one may say that the direction of the velocity vector is changing in the clockwise direction. That is, it becomes like that, and then like that, and then like that, and then like that, and so on. Now of course all this is from the perspective of the vector diagram which we have drawn over here, and this particular description of how the velocity changes nicely fits in with the actual observed data. That is, the velocity begins like that, quite high above the horizontal, and then it's going towards the horizontal in this picture, in this particular, at this particular time instant, and then it becomes horizontal at one point, then it goes below the horizontal, and then over here it goes more below the horizontal. So what we have effectively done is to understand why the direction of the velocity behaves in a certain way by assuming that the acceleration of the particle is in the downward direction. We didn't make that assumption, actually we proved it. And of course the vital thing to observe here is that the acceleration, which is actually in the vertically downward direction over here, it is never parallel to the direction of the velocity vector. If you look at any one of these velocity vectors, none of them is actually parallel to the acceleration. And so hopefully this particular example will help to develop confidence in the concept that the acceleration of a particle need not be parallel to the particle's velocity.